And now in this lecture we'll find out the radius of the small circle. In the drawing we have the right triangle ABC. We know that side AB of the right triangle ABC equals to 6 units in its length, side BC equals to 8 units. This is angle ABC, that is the right angle. Inside the right triangle ABC we have this small circle and this big semicircle, and our mission is to find out the radius of this small circle. So first of all we will define the relevant points to this question with letters. We will define the center of this small circle. This point is point P. We will define the center of this big semicircle. This point is point Q. We will define the point of tendency of tangent AB with this small circle. This point is point N. We will define the point of tendency of tangent AC with this small circle. This point is point K. We will define the point of tendency of tangent AC with this big semicircle. This point is point H. And finally, we will define the tangent point of this small circle with this big semicircle. This point is point L. Okay. In the next step, we will implement the Pythagoras theorem in this right big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle ABC, the hypotenuse is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. So I'll write it down. Here by PT is a version for Pythagoras theorem. So in the right triangle ABC, according to the Pythagoras theorem, AC square equals to AB square plus BC square. Repeat again, in the right triangle ABC, AC square equals to AB square plus BC square. The hypotenuse AC, we don't know the value of the hypotenuse AC, so we write as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 square, that is 36, plus BC square. BC is 8, therefore BC square is 8 square, that is 64. So in total we found out that AC square equals to 36 plus 64. 36 plus 64 is 100, so AC square equals to 100. We take out of this equation and finally get that the hypotenuse AC is equals to 10 units in its length. So write it down. The length of the hypotenuse AC is 10 units. Here we can actually implement rule 2. I'll repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle, and we have also, this is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common standpoint, point A, from this common standpoint, point A, we have two tangents to this small circle, tangent AN and tangent AK. And according to rule 2, they are equal to each other. That is to say, AN equals to AK. So, what is wrong? According to rule 2, tangent AN, actually, if you focus on this common sum point A, for this common sum point A, we have two tangents to the big semicircle, tangent AB and tangent AH, and according to rule 2, they are equal to each other. That is to say, AB equals to AH. So according to rule 2, tangent AB is equals to tangent AH. Rule 2. But it is given as a question that AB equals to 6, so we can write that AB equals to 6, and for this equation 6 equals to AB equals to AH, we will derive that AH is also equals to 6 units in its length. So this is tangent AH, let's say what AH, and it's equals to 6 units in its length. So I write it down. AH equals to 6 units in its length. What is the length of line segment HC? It is very easy to see from the drawing that HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. HC equals to 4 units in its length. In the next step, we join points Q and H together by a straight line. Point Q is the center of this big semicircle. Point H is the point on the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of the big semicircle as B, so QH equals to B, according to our definition. Here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing, we have a circle, and this is tangent AB, that is tangent to this circle at point M. In addition, we have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB. If this circle, whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing, we have the radius QB that equals the radius QH that is equal to B. The radius QH is going to point H, that is the point of tendency, tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees. And this again also equals to 90 degrees according to rule 1. Actually, by doing this construction, what we can do the right triangle QHC. In the right triangle QHC, we have this angle that belongs to the right triangle QHC. But this angle C also belongs to the big right triangle ABC. So angle C is a common angle that belongs to both triangles, to the small triangle QHC and to the big triangle ABC. So we will define the size of this angle C as alpha. and we focus on the right small triangle, triangle HQC. On the right small triangle HQC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees, that is the sum of the angles in any triangle. In the next step, we focus on the big right triangle, triangle ABC. On the big right triangle, triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, then the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that the big right triangle, triangle ABC, is similar to this small right triangle, triangle HQC. Okay. Triangle ABC is similar to triangle QHC. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC. In the right big triangle ABC, and it is equal to this angle, that is actually angle QHC. In the small right triangle HCQ. So repeat again, actually found out that angle ABC, the big right triangle ABC equals to angle QHC, the right big triangle CHQ. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha that belongs to both triangles. So I can write down that angle alpha is a common angle that belongs to both triangles. So if we relate to angle alpha as it belongs to the big right triangle ABC, it will be defined as angle ACB, and it equals to itself. So if you relate to this angle alpha as it belongs to the small triangle HQC, it will be defined as angle HCQ. Again, this equation means that angle alpha equals to itself. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle BAC. The right big triangle ABC, and it is equal to this angle, that is actually angle HQC. And the small right triangle HCQ. So repeat again. Actually found out that angle BAC in the right big triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. Okay, so actually it proved that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of the small right triangle HQC. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We proved that the right triangle ABC, the right big triangle ABC is similar. This is the sign of similar to the right small triangle, triangle HQC, according to angle similarity rule. And for the fact that the right big triangle ABC is similar to the right small triangle HCQ, we will derive the following relationship exists between their sides. We will derive that side AB is the big right triangle ABC over side edge Q in the small right triangle HCQ is equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Repeat again, we will derive that side AB in the big right triangle ABC over side HQ the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB is 6 over HQ. HQ is B, it is the radius of the big semicircle, and it is equal to BC. BC is 8 over HC. We already found out that HC equals to 4. So in conclusion, we found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So in total, we found out that 6 over B equals to 2. We multiply this equation by B and finally we get that 6 equals to 2B. We divide this equation by 2 and finally we get that the missing radius B is equals to 6 over 2, that is 3. Okay, so we found out that the radius B of this big semicircle equals to 3 units in its length. Here point Q is the center of this big semicircle, point B is the point of the big semicircle itself, therefore QB is the radius of this big semicircle, that is equals to 3. So I write it down. QB equals to 3 units in its length. In the next step, we will join points N and P together by a straight line. Point P is the center of this small circle, point N is the point of the small circle itself, therefore Pn is the radius of this small circle, the radius that you're looking for in this question. So we will find the radius of this small circle Pn as A. Again, A is the radius that you're looking for in this question. So the radius Pn is 1 to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will join points P and K together by a straight line. Line segment PK is of course the radius of this small circle, that is equals to A. You can implement here again all one because we have the radius PK that is on to point K, that is the point of tangent AC with this small circle. And whenever you have a radius that is on to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you draw two tangents to that circle, here, this is the current point, point P. From this current point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we created here this angle APB was created by drawing points, by drawing tangent PA and tangent PB to this circle. Okay, and according to rule 15, the angle bisector of this angle APB must pass for the center of this circle, that is actually point O. Again, whenever you draw two tangents to a circle, like here, from the current point P, you draw two tangents, PA and PB. By drawing the two tangents, we get here angle APB. According to rule 15, the angle bisector of this angle APB must pass through point O, that is the center of this circle. Okay, again, on rule 15, if from an external point of a circle you draw two tangents to that circle, then the angle bisector that will be created between the two tangents, the angle bisector of angle APB, the angle that was created between the two tangents is angle APB. So the angle bisector of this angle APB must pass through the center of the circle. So the angle bisector of this angle APB must pass from point O, that is the center of this circle. So I can actually implement rule 15 in our drawing. Why? Because in our drawing, if we focus on this current point A, from this current point A, we have two tangents to this small circle, tangent AN and tangent AK. By drawing the two tangents AN and AK, we get this angle, that is angle A. Again, angle A, this angle A was created by drawing tangent AN and AK to this small circle. According to rule 15, the angle bisector of this angle A must pass through point P. So the angle bisector of angle A must pass through point A. So must pass through point P. That is the center of this small circle. So PA is the angle bisector of this angle A, and it passes from point P, that is the center of this circle, small circle. If we define the side of angle A as 2 theta, then angle bisector PA bisect angle A into two halves. Each half must be equal to theta. Okay. Okay, again on rule 15, actually, by drawing from the current point A, by drawing tangent AN and tangent AK, we created this angle A. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. And so we're going to write down that the angle bisector of this angle A passes through point P, that is the center of this small circle. So I write it down. Yeah, we found out actually that the angle bisector of angle A passes for point P. That is the center of the small circle. We continue to focus on this common external point A. For this common external point A, we have two tangents to the big semicircle. We have tangent AB and tangent AH. And according to rule 15, so by drawing the two tangents AB and AH, we created the same angle A. Again, angle A, the same angle A is created by drawing tangent AB and tangent AH to this big semicircle. So, and according to rule 15, the angle bisector of the same angle A must pass from point Q, that is the center of this big semicircle. Again, the angle bisector of the same angle A that was created by drawing tangent AB and tangent AH to this big semicircle, the angle bisector of this angle A must pass from point Q, that is the center of the big semicircle. So here we draw the angle bisector of the same angle A must pass from point Q. Or in other words, actually, according to rule 15, we actually found out that QA is also the angle bisector of angle A. So we can find out that point Q is also the angle bisector of the angle bisector of angle A passes from point Q. Okay. The angle bisector of the same angle A passes also for point Q. That is the center of the big semicircle. So in conclusion, we found out that the angle bisector of this angle A passes through points P and Q, and the angle bisector of this angle A must also pass from point A, of course. So write it down. The angle bisector of the same angle A passes also for point A. So in conclusion, we found out that the angle bisector of this angle A passes for points A, P and Q. So write it down. Actually, in conclusion, actually found out that the angle bisector of angle A passes through points A, P, and Q. Okay. But we also know that the angle bisector of any angle is a straight line. Okay, the angle bisector of any angle is a straight line, and especially the angle bisector of this angle, angle A, is a straight line. So I write it down. The angle bisector of angle A is a straight line. And all the 3 points, they are all passing for the straight line that is the angle bisector of angle A. Or in other words, all the 3 points A, P, and Q, they are located on the same straight line. Okay. In conclusion, we found out that all the 3 points that are A, P, and Q, they are all located on the same straight line. Are located on the same straight line. And the straight line is, of course, the angle bisector of angle A. Okay. Or in other words, we can write down that line segment APQ is one straight line. Again, APQ is one straight line. APQ, or line segment APQ, is one straight line. And therefore, from the fact that APQ is one straight line, it means that this angle theta is a common angle that belongs to both triangles. Angle theta belongs to the big right triangle ABQ, and this angle theta also belongs to the small right triangle, triangle ANP. So I write it down. If we found out that angle theta is a common angle that belongs to both triangles. It belongs to the big right triangle, triangle ABQ. You can see that the angle theta belongs to the big right triangle, triangle ABQ, and angle theta also belongs to the small right triangle, triangle ANP. Okay. So, in the next step, we'll focus on the big right triangle ABQ. The big right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees it equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus theta, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right big triangle ABC is similar to this small right triangle A and P. We prove that the right big triangle ABQ is similar to this small right triangle A and P. So I can now. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABQ. In the right big triangle ABQ, and it is equal to this angle, that is actually angle A and P. In the small right triangle APN. So I repeat again. We actually found out that angle ABQ in the big right triangle ABQ equals to angle A and P, the small right triangle APN. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, this is the common angle that belongs to both triangles, so we can write down that angle theta equals to itself is a common angle that belongs to both triangles. So write it down. If we relate to angle theta as it belongs to the big right triangle ABQ, it will be defined as angle BAQ. And it is equal to itself, so if we relate to this angle theta as it belongs to the small right triangle ANP, it will be defined as angle NAP. Repeat again. This equation means that angle theta equals to itself. We just called to angle theta two different names. Angle theta equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle AQB, and the big right triangle ABQ, and it is equal to this angle, it is actually angle APN, and the small right triangle ANP. So repeat again, I actually found out that angle AQB, the big right triangle ABQ, equals to angle APN in the small right triangle ANP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually found out that all the triangles of the right big triangle ABQ are correspondingly equal to all the fingers of the small right triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. So if we found out that the right big triangle ABQ is similar, this is the sign of similar to the right small triangle, triangle ANP, according to angle similarity rule. And for the fact that the right big triangle ABQ is similar to the right small triangle ANP, we derive that the following relationship exists between their sides. We derive that side AB of the big right triangle ABQ over side AN of the small right triangle ANP is equal to side BQ of the big right triangle ABQ over side NP of the small right triangle ANP. So repeat again, we derive that side AB of the big right triangle ABQ over side AN of the right small triangle ANP equals to side BQ of the big right triangle ABQ over side NP of the small right triangle ANP. AB is 6 over AN. AN is the missing side, so we leave it as it is. And it is equals to BQ. BQ is 3, it is the radius of the big semicircle that is equals to 3 units in itself over NP. NP equals to A. A is the radius that we are looking for in this question. Radius of the small circle. So if we found out that 6 over AN equals to 3 over A, here we cross multiply this equation, and we get that 6A equals to 3AN. Here we divide this equation by 3 and finally get that the missing side AN is equals to 6A over 3 is 2A. So the missing side AN equals to 2A units in its length. This is the missing side AN. This is the missing side AN, and it is equals to 2A units. It is given us the question that AB equals to 6. We just right now found out that AN equals to 2A. Therefore, this missing 9, 7, and B must be equal to AN, that is 6. Yeah, this missing side NB must be equal to AB, that is 6, minus AN, that is 2A. So in total, NB equals to 6 minus 2A. So I write it down. This missing 9, 7, NB equals to 6 minus 2A units in its length. In the next step, we do a construction, that is to say from point P, we draw perpendicular on BQ. Again, from point P, we draw perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we created quadrilateral NPBZ. Inside quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBZ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a tetrahedral, not a square. So we write to quadrilateral NPBZ as a rectangle because it has 4 right angles. So write it down, this quadrilateral NPBZ is a rectangle. But we also know that the opposite sides of an rectangle are equal to each other. So an rectangle NPBZ, side NP must be equal to the opposite side BZ. But NPZ, therefore BZ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBZ, side NB must be equal to the opposite side PZ. But NB is 6 minus 2A, therefore PZ, opposite side PZ, must be also equal to 6 minus 2A. What is the length of the missing 97 QZ? QZ equals to BQ minus BZ. Again, QZ or ZQ equals to BQ minus BZ. So ZQ equals to BQ that is 3 minus BZ that is A. So in total, ZQ equals to 3 minus A. So I'll write it down. ZQ equals to 3 minus A. In the drawing, we have an external notch between this small circle and this big semicircle. That is to say they are touching each other externally at point L. And whenever you have an external notch between two circles, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their circles together must pass through their touching point. In the drawing, we have two circles. Those two circles have an external notch between them. That is to say they touch each other externally at this point P. The center of this circle, the small circle, is at point M. The center of this big circle is at point O. And the straight line that connects the circles together is of course the straight line MO. And this straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is the touching point, or MPO is one side line. Again, MPO is one side line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external notch between this small circle and this big semicircle. The center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is of course the straight line PQ. And according to rule 10, this straight line PQ must pass through point L, that is the touching point. Again, repeat again. This straight line PQ must pass through point L, that is their touching point, or P and Q is one straight line. If P and Q is one straight line, then PQ is also a straight line. But what is the length of PQ? PQ must be equal to PL plus LQ. Again, PQ equals to PL plus LQ. So write it down. PQ equals to PL plus LQ. Why? Because of the fact that P and Q is one straight line, it means that PQ will be equal to PL plus LQ. So PQ equals to PL. PL is the radius of this circle, that is the radius that we are looking for, and it is equals to A plus LQ. LQ equals to 3, it is the radius of this big semicircle, that is equals to 3 units. So in conclusion, we shall find out that PQ equals to A plus 3. PQ equals to A plus 3, so this is nice PQ, that equals to A plus 3. In the next step, I'll copy this right green triangle PZQ in a new page, and we will implement the Pythagoras theorem with this right triangle, triangle PZQ. Here by PT is the version for Pythagoras theorem. PZ equals to 6 minus 2A, ZQ equals to 3 minus A. And finally the bonus PQ equals to A plus 3. So finally, this is the right again triangle PZQ that I go from the original drawing, according to the Pythagoras theorem. And this right triangle PZQ. PQ square equals to PZ square plus ZQ square. Repeat again. PQ square equals to PZ square plus ZQ square. Plus ZQ square. So I'll write it down. So PQ square, that is the square of the hypotenuse, equals to PZ square plus ZQ square. PQ is A plus 3, therefore PQ square is A plus 3 square, and it is equals to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square plus ZQ square. ZQ is 3 minus A, therefore ZQ square is 3 minus A square. In conclusion, we found out that according to the Pythagoras theorem in the right triangle PZQ, A plus 3 square equals to 6 minus 2A square plus 3 minus A square. We open the brackets on both sides of this equation, and we get that A plus 3 square equals to A square plus 3 square, that is 9, plus 2 times A times 3, that is 6A. On the other side of the equation we have 6 minus 2A square, that is 6 square. 6 square is 36. And plus 2A squared, 2A squared is 4A squared. Minus 2 times 6 is minus 12, and minus 12 times 2A is minus 24A. Plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9. Plus A squared. Minus 2 times 3 times 8, that is minus 6A. So here we have A square on both sides of the equation, so A square will get cancelled. And we have also 9 on both sides of the equation, so 9 also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 6A. In the other side of the equation we have 36 plus 4A squared. Here we have minus 24A minus 6A is minus 30A. So in conclusion, we found out that 6A equals to 36 plus 4A squared minus 30A. Here we subtract 6A from this equation. So after we subtract 6A, this side of the of the equation we have to nothing, this is just say 0. On the other side of the equation we have 36 plus 4a squared and minus 48 minus 6a is minus 36a. So here we divide this equation by 4. And we get that 4a squared over 4 is a squared. Minus 36a over 4 is minus 9a. And 36 over 4 is 9. 0 over 4 is 0. In conclusion, we shall find out that a squared minus 9a plus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now, specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0. The variable that we are looking for is a, so x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 9. And finally, the coefficient c equals to 9. So actually, the only thing that is left to do is to put the data of our specific quadratic equation, this is to say this data, inside the general formula for x in order to find out the value of the values of a, because x equals to a. We'll do it now, and we get that x equals to a, so a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4, times c is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 over 2a. A is 1, therefore 2a is 2 times 1, that is 2. So a equals to 9 plus minus. Inside the root we have 81 minus 36, that is 45. So inside the root we have only 45 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus 4 to 45 over 2. This expression 9 plus 4 to 45 over 2 is greater than 3. So we actually found out that according to the first solution, for a, the radius a of this small circle is greater than 3 units. But the radius of this circle of this small circle cannot be greater than 3 units. Why? Because of the fact that the radius of this big semicircle equals to 3 units. And the big semicircle is definitely bigger than the small circle. And therefore, the radius of this big semicircle that is 3 must be greater than the radius of this small circle. Or in other words, the radius of this small circle must be less than 3 units. So, the solution that the radius of the small circle is greater than 3 is the incorrect solution, because the radius must be less than 3. So we cancel the solution, and we're left only with the second solution that is possible for A, for the radius of the small circle, that is A. So A, according to the second solution, equals to 9 1/4 of 45 over 2. So A equals to 9 and minus square root of 45. 45 is 9 times 5, so we substitute 45 by 9 times 5 divided by 2. So the radius A of the small circle equals to 9. The square root of 9 is 3, so inside the root we left only 5 divided by 2. So if we found out that the radius of the small circle A equals to 9 minus 3 times 4 to 5 over 2 units, so in terms of numbers, is equals to 1.146 units. That is less than the radius of the big semicircle, that is equals to 3. So finish the question. In the next step, we'll summarize the lecture. In this lecture, we found out the radius of this small circle. In the drawing, we have the right big triangle ABC. You know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. This is angle ABC, that is the right angle. In addition, we know that inside this big right triangle ABC, we have this small circle and this big semicircle. Our mission is to find out the radius of this small circle. So first of all, we defined the relevant points to this question with letters. We defined the center of this small circle, this point is point P. We defined the center of this big semicircle, this point is point Q. We defined the center, we defined the point of tendency of tangent AB with this small circle, this point is point N. We defined the point of tendency of tangent AC with this small circle, this point is point K. We define the point of tendency of tangent AC with this small, with this big semicircle, this point is point A. And finally, we define the touching point of this small circle with this big semicircle, this point is point L. In the next step, we implemented the Pythagoras theorem of this big right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. The hypotenuse in the right big triangle ABC is AC, so the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. Repeat again. According to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is, so AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total, we found out that AC square equals to 36 plus 64, that is 100. So AC squared equals to 100. We took out all of this equation and we found out that the length of the hypotenuse AC is equal to 100, it is 10. So AC equals to 10 units in its length. Here we can implement rule 2 because if we focus on this convex line point A, from this convex line point A, we have two tangents to the mixed semicircle, tangent AB and tangent AH. According to rule 2, they are equal to each other. That is to say, AB equals to AH. Repeat again, according to rule 2, AB equals to AH. But AB is 6, so can I tell that AB equals to 6? And from this equation 6 equals to AB equals to AH. We will derive that AH also equals to 6 units in its length. This line segment AH equals to 6 units in its length. What is the length of HC? HC equals to AC, that is 10, plus AH, that is 6. So in total, HC equals to 6 minus HC equals to 10 minus 6, that is 4. In the next step, we join points Q and H together by straight line. Point Q is the center of the big semicircle, point H is the point of the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of this big semicircle as B. So QH equals to B. Here we can implement rule 1 because we have the radius QH that is 1 to point H, that is the point of tendency of tangent HC with this big semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AC must be perpendicular to the radius HQ. AC is perpendicular to HQ. It means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do the right small triangle QHC. In the right small triangle QHC, we have this angle C that belongs to the right small triangle QHC. But this angle C also belongs to the big right triangle ABC. So angle C is a common angle that belongs to both triangles. We define the size of this angle C as alpha. Therefore, in the right small triangle QHC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the right big triangle ABC is similar to this small right triangle HQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is the angle alpha, that is a common angle that belongs to both angles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the angles of the right big triangle ABC are correspondingly equal to all the angles of the right small triangle HQC. Therefore, those two right triangles are similar to each other according to angle similar to. And again, we should find out that the right big triangle ABC is similar to the right small triangle HQC according to angle similarity rule. And from the fact that the right triangle ABC is similar to the small right triangle HQC, we derive that the following relationship exists between their sides. We derive the side AB in the right big triangle ABC or side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC or side HC in the small right triangle HCQ. Repeat again, we derive that side AB, the big right triangle ABC, or side QH, the small right triangle HCQ equals to side BC in the big right triangle ABC, or side HC in the small right triangle HCQ. AB 6, HQ is B, it is the radius of the big semicircle, that equals to B. BC is 8, and HC is 4. So in total, we have found out that 6 over B equals to 8 over 4. 8 over 4 is 2, so in total, we have found out that 6 over B equals to 2. We multiplied this equation by B and finally found out that 6 equals to 2B. We divided this equation by 2 and finally found out that the missing radius B of the small of the big semicircle equals to 3. So QH equals to 3, and QB is also the radius of the big semicircle, is equals to 3 units in its length. In the next step, we join points P and N together by straight line. Point P is the center of this small circle, point N is the point of the small circle itself, therefore Pn is the radius of this small circle. When you find the radius of this small circle, let's say A is the radius that we're looking for in this question. So Pn equals to A, you can implement here all 1, because we have the radius Pn, that is 1 to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Okay. Likewise, we join points P and K together by straight line. PK is the radius of this small circle, that is equals to A. Can implement here rule 1 because we have the radius PK, that is 1 to the point of tendency of tangent AC with this small circle. Whenever your radius is 1 to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is rule 15. Please click on rule 15. According to rule 15, from example point of a circle, you draw 2 tangents to the circle, then the angle that will be created between the 2 tangents, its angle bisector must pass through the center of the circle. So, in the drawing, we have, this is the connection point, point P. From this connection point, point P, we have 2 tangents to the circle, tangent PA and tangent PB. By drawing the 2 tangents PA and PB, we get here this angle. Again, angle APB, created by drawing tangent PA and tangent PB to this circle. So according to this rule 15, the angle bisector of angle APB, again the angle bisector of this angle APB, must pass through point O, that is the center of this circle. Again, the angle bisector that was created by 2 tangents, it must pass through point O, that is the center of this circle. We can implement rule 15 in our drawing. Why? Because in our drawing, we have, this is the connection point, point A. From this connection point, point A, we have 2 tangents to this small circle, tangent AN and tangent AK. By drawing the 2 tangents AN and AK, we created this angle A. This angle A, repeat again, this angle A is created by drawing tangent AN and tangent AK to this small circle. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So if you write down the three, according to rule 15, the angle bisector of angle A passes through point P. Angle bisector of this angle A passes through point P. If we define the size of angle A is 2 theta, then the angle bisector PA bisects angle A into 2 halves. Each half must be equal to theta, of course. Likewise, we'll continue to focus on this convex point, point A. From this convex point A, we have 2 tangents to this big semicircle, tangent AB and tangent AH. By drawing the 2 tangents AB and AH, we created the same angle A. Again, angle A was created by drawing tangent AB and AH to this big semicircle. And according to rule 15, the angle bisector of this angle A must pass also from point Q, that is the center of the big semicircle. Again, the angle bisector of this angle A must pass from point Q, that is the center of this big semicircle. Repeat again, actually found out that according to rule 15, the angle bisector of the same angle A passes also from point Q. That is the center of the big semicircle. So the angle bisector of angle A, in total it passes from points P and Q. But the angle bisector of angle A must pass also from point A. It's trivial that the angle bisector of this angle A must pass from point A. So you can write that the angle bisector of angle A passes also from point A. In conclusion, if you found out the angle bisector of this angle A passes from points A, P and Q. I repeat again. In total, if we found out that the angle bisector of angle A passes from points A, P and Q. Okay? But the angle bisector of any angle is a straight line. Okay? Yeah, the angle bisector of any angle is a straight line, and therefore the angle bisector of angle A is a straight line, of course. So, in conclusion, we found out that all the 3 points A, P, and Q, they are located on the same straight line. And the straight line is the angle bisector of angle A. Okay? All the 3 points A, P, and Q are located on the same straight line. And the straight line is the angle bisector of angle A. Okay? All the 3 points A, P, and Q are located on one straight line. In other words, we can also say that line 7 APQ is one straight line. Again, line 7 APQ is one straight line. And again, this line 7 APQ is one straight line. If line 7 APQ is one straight line, it means that this angle theta is a common angle that belongs to both triangles, to the big triangle ABQ and the small, and also to the small triangle, triangle A and P. Okay, again, if we found out that angle theta is a common angle that belongs to both triangles, it belongs to the big right triangle ABQ, and the angle theta also belongs to the small right triangle, triangle A and P. In the next step, we will focus on the right big triangle, triangle ABQ. The right big triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees. At 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus theta according to the same rule, then the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right big triangle ABQ is similar to the small right triangle, triangle A and P. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write down that the angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the three angles of the right big triangle ABQ are corresponding equal to all the triangles of the small right triangle A and P. Therefore, those two right triangles are similar to each other according to angle similarity rule. So if in again, we found out that the right big triangle ABQ is similar to the small right triangle A and P according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right big triangle ABQ over side AN of the small right triangle A and P equals to side BQ of the right big triangle ABQ over side NP of the small right triangle A and P. Okay, again, we derive that side AB of the big right triangle ABQ over side AN of the small right triangle NP equals to side BQ of the small equals to side BQ of the big right triangle ABQ over side NP of the small right triangle NP. AB 6, AN is the missing side, so we leave it as it is. BQ is 3 and NP is A. So if we found out that 6 over AN equals to 3 over A. Here we cross multiply this equation, and finally found out that 6A equals to 3AN. Here we divided this equation by 3, and finally found out that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So this is the missing side AN. Is equals to 2A units in itself. AB equals to 6, AN equals to 2A, therefore the missing let's say that NB must be equal to AB, that is 6, minus again, that is 2A. So in total, NB equals to 6 minus 2A. In the next step, we did the construction, that is to say, from this point P, we go perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, created quadrilateral PNP BQ. Inside quadrilateral NP BQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 450 again, in total they must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this 450 again must be equal to 90 degrees in size. So inside quadrilateral NPBQ we have 4 right angles, and then according to rule 5, any quadrilateral that has 4 right angles must be this rectangle and not a square. So we need to this quadrilateral NPBQ is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So the rectangle NPBQ, side NP must be equal to the opposite side BZ. But NP is A, therefore BZ must be also equal to A. Likewise, according to the sum rule, in the rectangle NPBQ, side NB must be equal to the opposite side PZ. But NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of the missing side ZQ? ZQ equals to BQ minus BZ. BQ is 3, BZ is 8, therefore in total ZQ equals to 3 minus 8. Here we can implement rule 10 because we have an external length between this small circle and this big semicircle, that is to say they are touching each other externally at point A. And whenever you have an external length between two circles, you can implement rule 10. So I'll click quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass for their touching point. So in the drawing we have two circles and they have an external length between them at point P. That is to say they touch each other externally at point P. The center of this circle is here at point M. The center of this mixed circle is here at point O. The straight line that connects their centers together is of course the straight line MO. So this straight line MO must pass for point P, that is their touching point. Again, the straight line MO must pass for point P, that is the touching point, or MPO is one straight line. Again, MPO is one straight line. So we can actually implement all 10 in our drawing. Because in our drawing we have an external length between the small circle and the big semicircle. The center of this small circle is at point P. The center of this big semicircle is at point Q. The straight line that connects the centers together is the straight line PQ. According to rule 10, this straight line PQ must pass from point L, that is the touching point. Again, the straight line PQ must pass from point L, that is the touching point. Or PLQ is one straight line. Again, PLQ is one straight line according to rule 10. If PLQ is one straight line, means that PQ also is a straight line. But what is the length of PQ? PQ equals to PL plus LQ. And PQ equals to PL plus LQ. PL is A, and LQ is 3. So in total, PQ equals to A plus 3. In the next step, by proving the right green triangle PZQ in a new page, and implemented the Pythagoras theorem on the right green triangle PZQ. This is the right green triangle PZQ that I copied from the original drawing. According to the Pythagoras theorem, this right triangle PZQ, PQ square equals to PZ square plus ZQ square. PQ is A plus 3, therefore PQ square is A plus 3 square, and it is equals to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square. Plus ZQ square. ZQ is 3 minus 8, therefore ZQ square is 3 minus 8 square. So in conclusion, found out of 3 that A plus 3 square equals to 6 minus 2A square plus 3 minus 8 square. We open the brackets on both sides of the equation and finally found out that A plus 3 square equals to A square plus 3 square, that is 9, plus 2 times A times 3, that is 6A. The other side of the equation we have 6 minus 2A square. 6 minus 2A square equals to 6 square, that is 36. Plus 2A squared, that is 4A squared, plus 2 times 6, that is minus 12, times 2A. Minus 12 times 2A is minus 24A, and we have 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times A is minus 6A. So here we have A squared on both sides of the equation, so a square will get cancelled. We have 9 also on both sides of the equation, so 9 also will get cancelled. After we cancel those two expressions, in this side of the equation, we have 20 which is 6a. In the other side of the equation, we have 36 plus 4a squared. Minus 24a minus 6a is minus 38. So in conclusion, we have found out that 6a equals to 36 plus 4a squared minus 48. Here we subtracted 6a from this equation, and we found out that in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 36 plus 4a squared, minus 48 minus 6a is minus 26a. Here we divided this equation by 4, and found out actually that 4a squared over 4 is a squared, minus 46a over 4 is minus 9a, and 36 over 4 is 9. So in conclusion, actually found out that a squared minus 9a plus 9 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that you are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus 4 to b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a, so x equals to a. The coefficient a equals to 1, the coefficient b equals to minus 9, and the coefficient c equals to 9. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for a, or for x, and we find out the values of a, because x equals to a. We did it, and found out actually that x equals to a, so a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus 4 to b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c is 9, so minus 4 times 9 is minus 36, divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So we have found out that a equals to 9 plus minus square root of 81 plus 36 is 45. So a equals to 9 plus minus square root of 45 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2. 9 plus square root of 45 over 2 is greater than 3. So according to the first solution, the radius a of this small circle is greater than 3. But the radius of this small circle cannot be greater than 3 because of the fact that the radius, why? Because of the fact that the radius of the big semicircle equals to 3, and the big semicircle is definitely greater than the small circle, and therefore the radius of the big semicircle that is 3 must be greater than the radius of this small circle. In other words, the radius of this small circle must be less than 3. It must be smaller than 3. But according to the first solution, the radius of the small circle is greater than 3. So this solution is the correct solution. We cancel the solution, and we have to leave the second solution that is possible for the radius a of the small circle. A equals to 9 minus 4 to 45 over 2. So a equals to 9, and 45 is 9 times 5, so we substitute 45 by 9 times 5 divided by 2. So a equals to 9, and the square root of 9 is 3. Inside the root we left only with 5. So according to the second solution, for a, the radius a of this small circle equals to either 9 minus 3 times square root of 5 over 2 units in its length, or in terms of numbers, the radius of this small circle a equals to 1.146 units. That is definitely less than 3 units. That is the radius of this big semicircle. Repeat again, the radius of this small circle equals to 1.146 units. Okay, thank you very much.